Okay, we can use a qualitative or a quantitative way to compare the acidity of protons on our compounds. And first we're going to talk about the quantitative way by comparing the pKa values. So let's go back and revisit equilibrium. At equilibrium, the rate of the forward reaction and the rate of the reverse reaction are the same, and the concentration of the reactants and products does not change. So we can write an equation that looks like this. The chemical equilibrium is equal to the products, which we will put like this, divided by the reactants. Now, in the equations that we're going to be doing, the concentration of water is not going to be changing because there's so much water around. So we can change this equation and write it as a Ka. And we're going to write basically the same equation, but we'll leave water out of it. Now, we would expect strong acids to have a high Ka, or a large because we'd expect a strong acid to make a lot of these products and not have very much of the reactant left. And we would expect weak acids to be just the reverse. A weak acid is going to have a small Ka. Okay? These numbers are going to vary from 10 to the 10th down to 10 to the minus 50th. And that's a really big range. And it makes it awkward to deal with numbers that big. And so we will take it and we'll take the negative log and make a pKa. So the pKa is equal to the negative log of the Ka. And we would expect that, therefore, that strong acids are going to have a small pKa. Because they have a large Ka, the negative log of it would make it a small pKa. And that weak acids will have a larger pKa. Okay? So you can remember that strong acids have a small pKa because with pH, the small numbers are more acidic. That helps you. And if you were in class, you'd be receiving a paper copy of this chart that has a lot of the compounds that we'll be using. And for acids, it's fairly straightforward. You're just going to compare the pKa's. So here we're asked which is the more acidic compound, and we look on our chart and we see that the pKa here is 9.9 and the pKa for water is 15.7. Remembering that the smaller number means that it's more acidic, we have that as our more acidic compound. We look at the next one. We've got water and this alcohol. And for water, we have 15.7. For the alcohol, we've got 18. We'd expect the one with the smaller pKa to be more acidic, and so this time water is more acidic. Lastly, we've got ammonia and this alkyne, and we have The alkyne is 20, has a pKa of 25, and we have 38. The one with the smaller is the more acidic, and so that's what we get. Okay, we can also use pKa to compare bases. To compare bases, we'll want to draw the conjugate acid, and then remember that the stronger acid will make the weaker base. So you can think of this as a tug of war between the acid and the base. Who's going to end up with this proton that nobody wants? The stronger acid is going to be better at giving it away, and it's going to have a weaker base. The base is going to be more able to keep it. Okay? So let's look at these as our examples. I'm going to pull another piece of paper in here to give myself some more space. We're going to write the conjugate acid for this compound is going to be, all we're going to do is add a proton. That makes the conjugate acid. And here we have the conjugate acid of this. It's going to be ammonia. And then we can look up our pKa's. The pKa for this compound is 25, and for this it's 38. And we know that the stronger acid, which is this one, will have the weaker base, and so we're asked here for the stronger base. So we're looking for the, if we're looking for the stronger base, we're looking for the weaker acid, which is this one. Okay. All right. So let's do this one. We've got, when we draw these out, we're going to get 2 alcohols. We look up the pKa's for these compounds. We come up with 18 for this one and 16. That makes this the stronger acid. pKa is lower. That makes it also the weaker base. So this one is the stronger base. I'm sorry. This is the stronger base. All right, let's look at one more. Little arrow, we'll get rid of that. All right, we're going to have a compound that looks like this, and one that looks like that. We look on our table, and we see that this one is minus 7.3, and this one is minus 1.74. So that makes this one the stronger acid. So stronger acid goes with the weaker base. This is the weaker acid and the stronger base. And our problem asks us for the stronger, so that would be the answer. Okay, we can also use our pKa values to predict the position of equilibrium. The equilibrium will always favor the formation of the weaker acid. And again, if you're thinking of your push and pull, the strong acid is going to be successful at getting rid of its proton. And when it does, it's going to make the other side. So the equilibrium is always going to favor the formation of that weaker acid and that weaker base. So if we look at our example, we have our base. We have an acid with a pKa of 15.7. And on the other side, we have a pKa of 18. So the equilibrium is always going to favor the weaker acid. That's this one.